In the previous video, we discussed about relative displacement when bodies have constant velocity, and in this video we are going to find displacement between two bodies having variable velocity subjected to common acceleration. So let's get started. Okay, so now we have the case of variable velocity. The problem states that two balls are thrown from the top of a tower, one in the east direction with a horizontal velocity of 4 meters per second, and the other ball is thrown towards west with a horizontal velocity of 3 meters per second, and we have to find the distance between them when their velocities become perpendicular to each other. So as you know, the trajectory of the ball would be parabolic. Its horizontal velocity will not change, but its vertical velocity will grow from 0 to gt in downwards direction in time t. And similarly, this ball would have a vertical velocity of gt in downward direction when it reaches this point. Its horizontal velocity will remain at 3 meters per second in minus x direction. This is x and this is y. So after time t, the balls reach these two locations and we have to find the distance between the two. So let us write down the velocity vectors. v1 would be 4i minus gtj, and v2 would be minus 3i minus gtj. And what shall be the relative velocity of the first ball with respect to the second would be v1 minus v2, and that will work out to 4i plus 3i because the j components both are gt and they would cancel out, and therefore we shall have the relative velocity of first ball with respect to second as 7i. That is, this is now constant. There is no term containing t, and throughout the motion of the two balls, the relative velocity remains constant. This is an important point because it makes our calculation simpler. After time t, this distance d would simply be 7 times t because the initial displacement is 0, and therefore d would be equal to the constant relative velocity 7 times the time it takes from this position to this position. Now what is meant by the velocities becoming mutually perpendicular? It means that at certain point the velocity v1 has an angle of, let's say, theta 1 with vertical, and the velocity of the second ball v2 makes an angle theta 2 with vertical, and therefore theta 1 plus theta 2 would be equal to 90 degrees. So when two vectors are perpendicular to each other, we know that their dot product is equal to 0. This is the basic property of vectors. So let us find out the dot product of v1 and v2. The dot product v1 dot v2 would be this vector dot this vector. We multiply each of the terms, and we know that I dot I is 1 and I dot j is 0. So these two terms would become 0, and we would be left with minus 12 and g square t square. And since v1 and v2 are mutually perpendicular, v1 dot v2 would be equal to 0, and therefore this expression would be equal to 0, and that will yield t is equal to under root 12 upon g. So now we know that it takes so much of time to reach this point, and at this point the two velocity vectors are mutually perpendicular, and therefore the distance between them would simply be the magnitude of the relative velocity times t, because the initial displacement is 0 and the relative velocity is constant throughout the motion. So d would work out to 7 times square root 12 upon 9.8, which is g, and will give us 2.5 meters. So that's the answer. Let's tackle one more case of variable velocity. In this example, again we have the case of variable velocity. Two objects are thrown from the same location, one vertically up with a velocity of v0 and another at an angle of 60 degrees with the horizontal, and its magnitude is also v0, and we have to find the distance between them 1.7 seconds later. v0 is 25 meters per second and their initial displacement is 0 because they are thrown from the same location. So let us find out the initial velocities of these two objects and the relative velocity. And as we saw in the previous case, both the objects are subjected to the same acceleration, the gravitational acceleration of g acting downwards, and therefore the relative velocity would be constant. So this is the initial velocity of object 1. It is going vertical, therefore it is VOJ. The second object has a parabolic trajectory and its initial velocity U2 is V0 cos theta I and V0 sin theta j. And the difference between them, that is the relative velocity of the first object with respect to the second, is U1 minus U2, and we subtract this vector from this vector and we get this expression, and we notice that there is no t term. That means this is constant. So this is constant. So relative acceleration, as you know, is 0. When an object moves in a straight line with a uniform acceleration, you know that the position x at time t is equal to its position with respect to origin at t is equal to 0 plus the initial velocity times t plus half acceleration a t square. You are familiar with this equation of motion. A similar equation applies for relative displacement also. Now here r1 oblique 2 is the relative displacement at time is equal to t. This is the relative displacement at t is equal to 0. Instead of u, we have now the relative velocity of 1 with respect to 2 times t plus half. Instead of a for the single object, we now have the relative acceleration of 1 with respect to 2. Now in this particular case, as we found out here, the relative acceleration is 0, so this term would become 0. The relative displacement at t is equal to 0 is also 0, so this term also is 0. So the relative displacement at time t would be equal to the initial relative velocity, which remains constant, times t. So this is the vector notation for the displacement at time is equal to t, and now we take its magnitude. So that will be equal to square root of the I component square and j component square. That is what this expression says. And now we plug in the value of t, which has been given as 1.7 seconds, and we get the result as 22 meters. So that's our answer. So the key point is that the equation of motion for relative displacement is quite similar to the equation of motion of a single object moving in a straight line with a uniform acceleration, and we can use that to compute the relative displacement. So I hope you liked the examples that we dealt with in this video, and if you like them, please share the video with your friends and give a like, and do not forget to subscribe to the channel if you haven't done so as yet. So thanks for watching, and see you in the next video.